So let's talk about the 5G requirements, the new network, the new traffic, and the new challenges. Well, first of which, let's talk about, again, in 4G, I mentioned this earlier in relation to CPRI. 4G, everything was treated as best effort, meaning they were all, regardless of the type of application that you are running over the air, be it voice, video, data, streaming, whatever it may be, it was all treated the same once it hit the radio. It was all put within an antenna container, within a CPRI traffic or a CPRI transport frame, and then it was transferred via CPRI, including with the IQ data, down to the baseband unit. When we move forward to 5G, one of the big changes, and I mentioned this earlier, it gives you flexibility to provide different qualities of service. So provide quality supporting each scenario. Jeff and I both mentioned a couple of these scenarios, but what we're basically breaking down is to 3 distinct applications. First of which is enhanced mobile broadband. That's everything from your high bandwidth up to 20 gigabits per second. And as Jeff mentioned in a previous presentation, that's not just to a single device, but that could be it to the home as a last mile application. That could be private service, private 5G within a warehouse, within an enterprise, something of that nature. So when we think of 20 gigabits, it's not just to a phone. We're talking about larger scale commercial applications. We also talk about machine-to-machine type communication. So this could be your Internet of Things, but think a little bit broader than that. Smart manufacturing, that's one of the big applications that we're seeing for machine-to-machine type of communication. What does that mean? That means I have 5G radios within a manufacturing plant, and all of my devices on that manufacturing plant, instead of being hardwired to a connection, they're all communicating over the air through a 5G connection. That connection is then going to a server. This could be a mobile edge computing, an MEC that's located close by, where that server application is controlling all of the devices on the manufacturing floor. Think about the advantages to that from a wireless perspective. If you have a manufacturing that's all being controlled over the air, you have the ability to dynamically adjust your manufacturing plant simply by moving these various devices around. They're not hardwired together, they're not associated with a specific line, so you'd be able to adjust that manufacturing in near real time. So that's just an example of another machine-to-machine type. And then the ultra-reliable low-latency communication. We've touched on this pretty deeply earlier, everything from that remote operation scenario, the V2X, vehicle to everything. And there's a few more of those that we'll bring up later on. But the point I'm trying to make here is, as we call this slide new traffic and new challenges, is that each one of these scenarios are very different as far as requirements are. So what I mean by that is when you look at enhanced mobile broadband, it's all about throughput. Whereas when you look at machine-to-machine communications, it's all about the high number of connections. And then finally, when you look at ultra-reliable low-latency communication, it's all about speed or latency. How fast can I get that traffic? 3 profiles, 3 requirements, but all have to be supported over the same network. How do we get that accomplished? Well, you need an ultra-flexible network, and that's where new terms for 5G were introduced, such as network slicing. So as you can see on this slide on the left-hand side, what network slicing is referring to is being able to take those 3 different applications, once they're terminated on the radio, prioritizing those applications, and although they are on the same physical network, they're treated very differently depending on how they're prioritized by the network itself. So you combine that with that of virtualized technology, and I mentioned this briefly in my early presentation, that of software-defined networks and network virtualization, is you have a self-dynamically adjusting network. Now this is ideal, but we're not ready for this yet. In the early stages of 5G, we're more defining the network slicing first, being when you take those 3 different applications, enhanced mobile broadband on top, machine-to-machine communication in the middle, ultra-reliable low-latency communication on bottom. I'm taking those 3 distinct applications, I'm prioritizing them once they reach my radio head, and then I determine where I have those terminated within my physical network. That could be within my radio, that could be within my baseband unit, that could be farther out into the core. Now, Jeff made an example in his presentation about where do we see the IQ data? And in some cases, you don't see it anymore. Why? Because that's being terminated in the radio. That's going back to this specific network slicing, specifically with the ultra-reliable low latency communication, that when I know that has the highest latency requirement, meaning it has to travel the shortest amount of time, I'm having that IQ data terminated directly in my radio so I can turn that traffic around quickly, right? Whereas if I have another application such as that high bandwidth streaming for enhanced mobile broadband, I don't have to terminate that IQ data within the radio. I can prioritize that to have that go a little bit farther out, be it my distributive unit that could be within my CRAN hub, that could be co-located at my tower. I have the flexibility to determine where I want to put that. That's the idea behind network slicing, being able to prioritize those applications and determine where within my physical network I want that to terminate. The next step would be that software-defined network that once I've determined that, now I want my network to manage itself. That in the event of bandwidth rising and falling, where demand increases and decreases, allow it to dynamically allocate that bandwidth within my Next Generation Fronthaul Interface to meet those applications' needs. Does that make sense so far?
Yeah.
Okay. Yes?
When you terminate this, some of the services like automotive, for example, very early, is there a question about, let's say, somebody higher, like government, requiring oversight?
So if I understand your question correctly, is if you lose that, if you're using that ultra-reliable low latency communication application like V2X, and you're having that terminate within the radio where you lose that visibility to that IQ data, is there a question of government oversight, being able to determine that signal? There is, depending on like FCC regulations and so on, but that's not to say that the radio equipment itself doesn't have the ability to see that data. For example, in certain radios that are being developed today, those that do terminate that IQ data within there do have their own capabilities of being able to provide some of that information to export that for visibility purposes. So it's not to say that it's not available. The challenge becomes the cost associated with it. Do you have that functionality built in? The other question is, as far as when you're dispersing this over a size of a network, how many of these radios do you want to have that capability to meet that requirement? Does that answer your question?
Yes, actually, if you look at the amount of data that's coming out of, let's say, all these cameras, for example, it's not possible to store all that information in today's data centers, for example.
Correct.
They will run out of all this.
Well, that's why, exactly. So when you have that, so the question becomes, when you start having video applications and so on, when you start looking at the sheer number of different connections, how would you be able to manage all of that data, right? And that's where that mobile, actually that goes into my next slide here with the mobile edge computing, that's where the need to deploy these field data centers, these mobile edge computings to the edge to capture that data and be able to store it. Now, not all of it's going to be stored. There's obviously going to be cycling in so much period of time before that's flushed. But this goes into that next application for security, as you were just mentioning, automotive, medical care, and so on. This is the application out of the three that I've mentioned. This one is by far the one that's the most challenging to support from 5G perspective. And I'll bring up some of those challenges later on, but you can see this in the immediate reason. In order to support some of these, here's the biggest one. For the ultra-reliable low latency communication, per the standard, it's defined that it has to have less than 1 millisecond end-to-end time latency. Less than one, we're gone are the days of 40 and 50 milliseconds. Now we're talking about less than 1 millisecond in order to meet this requirement. And that's the total from the device to that of the termination. Now let's look at just the optical, the wireline portion. Less than 100 microseconds. So that's, and for those of you that are familiar with 4G, this isn't very different from when we started implementing LTE, and we had to deal with how close the baseband unit needed to be in relation to the radio head, right? For CPRI, that was in a neighborhood, what was the I think it was like 15 kilometers or something of that nature, where the baseband unit had to be within distance of fiber to that of the remote radio head. That was a latency issue, and that had to do with the IQ data. This is very similar, but just much tighter. So what's one of the ways that we are going to be able to get the data from the radio, once it terminates on the radio, to that of the servers or the switches, or I should say to the data center, and back within this amount of time? That's where mobile edge computing came in. So as you can see in this picture here, in the original diagram here, you had cloud servers. These are what traditionally held all of your applications, everything from your streaming video to your Facebook and so on, that's serving a certain geographic area. That was out in the edge of the mobile network, and then I had to traverse a course over maybe like the backhaul or something of that nature in order to get into all of your users. Now they're taking that cloud server and they're moving it into the mobile edge computing much closer to the edge, therefore providing lower latency for processing nearby versus farther distance where it was processed at the network side. So Jeff, one of the unique applications that we're starting to see, and there's a lot of different ways you can go with this, but I'll give you an example. There's a tourism company located in Rome. And what this tourism company is doing is they're working with like Facebook Oculus, the new goggles, or as well as there used to be Google Glass, but the similar augmented reality goggles, where what they're designing is, as a tourist, you can go to this company, you rent the goggles, you put on the goggles and you walk around the Colosseum. And as you're walking around the Colosseum, in real time, the goggles are augmenting reality and changing the view of the Colosseum as to what it looked like 2,000 years ago, while playing the audio as to what you're looking at and explaining that part of the Colosseum, all in real time. Now think about this from an application perspective. What are certain things that you must have? First of which, you got to have the bandwidth, right? Because you're streaming all of this augmented video to these goggles in real time. Second, you need low latency, because obviously if I'm looking at this part of the Colosseum, if I take 5 steps over and it's still telling me and showing me what I'm looking at here, it's not going to give me the real world experience I'm looking for. It has to update in real time. And then third, you also need to have the massive machine-to-machine or Internet of Things, because I'm going to have thousands of tourists all walking around the Colosseum at the same time in different locations looking at different things. It's a very unique 5G application. So the reason I bring that up here is if I use that same application and the Colosseum's cloud servers to support all this were on the other side of Rome, what am I doing? One, I've increased the latency. I'm putting a tremendous strain on my optical network because I have all these users in, at the Colosseum all taking up bandwidth to talk to my data center on the other side. And latency, what I mentioned, latency, bandwidth, as well as, excuse me, I'm sorry? Reliability. Yeah, well, yeah, with the glitchiness of the reliability. So by putting a mobile edge computing as close to the Colosseum as possible and putting up 5G millimeter wave radios around the Colosseum, I got the bandwidth, I've got massive number of connections, and I've got the low latency because I have everything being computed or processed right there close to my central location. Now for my users away from the Colosseum, they're using different bandwidth that's not being taken by that of that tourism company. Does that make sense? So that leads me into my next example here, is that just like the example with the Colosseum, one application may fall into 3 different applications. It's not just going to be ultra reliable. You're going to see that certain applications actually require multiple requirements. So what we say here is 5G is just basically a combination of 4G with the addition of social infrastructure. So the augmented and virtual reality video service, I just described that application. High bandwidth, low latency, massive connections. But you'll also see industrial IoT. That's that smart manufacturing that I just talked about. Again, low latency, just like augmented video. Massive connections, just like augmented video. But they have another requirement, secure and highly available. Do I want anyone to be able to tap into my 5G network that's controlling my manufacturing floor? Absolutely not. Then you have the remote operation and vehicle V2X, vehicle to everything, similar requirements. What's the point I'm trying to get at here? Well, look at the bottom of this slide. I do a comparison of what these requirements were at 4G compared to 5G. And this is where you really start seeing the challenge. First of which you see in the enhanced mobile broadband, you see the targets up to 20 gigabits per second. That's anywhere from 10 times to 100 times the bandwidth requirements of 4G. You look at ultra-reliable low-latency communication. We just saw this one. We saw less than 1 microsecond end-to-end. That's 1/10 of what the requirement was for 4G. And then finally, we see the massive machine-type communications, the Internet of Things. 1 million devices per square kilometer. That's where Jeff was giving me a hard time because I kept it with kilometers. But 1 million devices per square kilometer, or 10 times to 100 times that of 4G. I mean, we're already seeing that now. I mean, how many of us carry around not just 1, but 2 or 3 smart devices that are connected, right? That's not uncommon, and we're just going to see that continue to explode. So now that we've talked a little bit about 5G as it relates to the applications, and I gave you an example, and how they have multiple requirements. We also discussed briefly about network slicing and prioritizing that traffic. Let's go into these 2 different phases that I mentioned. So again, as I mentioned, the first phase has to do with release 15, 3GPP release 15, which is currently today. We're seeing early services being deployed in the US, Korea, Japan. You're seeing a lot of press releases and stuff, and you're seeing devices with incredible download speeds. When they're saying that for this initial 5G, we're really only focused on one application. That's the enhanced mobile broadband, the high bandwidth application, because that's really the first step that we're taking into 5G. That's not to say we're not also doing the UR-LLC application, ultra reliable low latency communication, nor that saying that we're not doing our machine-to-machine type communication. But what we are stating is once we get to release 16, that's integrating full 5G. That's taking the enhanced mobile broadband that we already have established today and adding the other requirements. Lots of connections, very low speed. Now that's the pain point. That's what everyone's worried about. I mean, just think about an expressway, right? When you only have 1 car going on the expressway, that's a very fast expressway. You don't have any issues with latency. You don't have any issues with traffic. Now you're going to pile that expressway with a bunch of moving vehicles, an accident or 2, add some congestion, and then try getting an ambulance through there. Now you've got a real issue. That's release 16. Can you tell I'm from Chicago? I always focus on traffic. It's no different out here. So what does that mean? First part of phase 1, as we're working with our customers today, and this is, now I'm going to start talking about the real world scenarios and the type of applications that we're testing today. When it comes to enhanced mobile broadband, it has everything to do with, as Jeff and I both talked about, TDD, time division duplexing. And as Jeff also mentioned in his presentation about how when you're looking at the time slots, everything is in relation to time, in microseconds. And if you are just a few microseconds off in any direction, you're looking at a different time slot. And if you're trying to transmit when they're receiving, you lose everything. It's all about timing. So when it came to us in testing in the field, what we're being asked is, how can we verify our timing? More specifically, how do we verify our synchronization? That's going to be phase one. Phase two, we start talking about latency. And going back to that example that I just made, what happens when I add all of this traffic into my network and then I have my ultra-reliable low latency communication? The traffic that must be received within a certain time threshold. How is that going to be affected? So let's go into phase one. Phase one, again, enhanced mobile broadband. That's the high bandwidth up to 20 gigabits per second. How are we going to accomplish that high bandwidth? Well, again, we're moving away from frequency division duplexing to time division duplexing. This allows us to transmit over the same spectrum or wavelength, but being able to do it at different times, an uplink and a downlink. Then we can add more channels to it. What does this mean? Things such as multiple base stations communicating through coordinated multipoint. That's how we're going to get that bandwidth. That combined with TDD. Here's a challenge. If the synchronization is poor, and I've shown this earlier, 3 microseconds or better accurate time synchronization. Why is it 3 microseconds or better? Well, as Jeff showed earlier, depending on what your carrier group is, that's how much spacing you have to work with. If your synchronization is off, your time slots will not align. That results in situations like you see on the bottom left, where your phone or the tower, depending on the two sites, one tower is expecting uplink, the other one's expecting downlink, but it's at 2 different times. There's a collision there, or synchronization. One of the first challenges when we were doing this in the field is we're working with a service provider who's deploying 5G, and one of the first issues that they ran into was synchronization issues. How are they going to get their sites synchronized? Now again, with GPS, it's not an issue. The challenge was what happens when they lost GPS. So I'm not going to ask you to read through this whole slide, but here are the requirements based out of the standard. So what I did was I've taken the actual synchronization requirements straight out of the 3GPP standard and I posted it on here. I showed 2 different standards. One is for LTE Advanced, which is LTE TDD. The other one is for 5G, which is already TDD. And you'll see highlighted in red is my cell phase synchronization requirement of less than or equal to 3 microseconds. And you see down here, that's for LTE Advanced, and then you see the same thing for 5G. Phase synchronization accuracy at the base station antenna connectors shall be better than 3 microseconds. Okay? So the diagram on the bottom left here basically shows your reference clock in the middle here, distributing the timing to 2 different towers, 2 different cells. The time between the clock and that of the tower or that of the cell must be within 1.5 microseconds. That's between the reference clock and that of the base station itself. Between base stations must be within 3 microseconds. So you notice there's 2 different requirements there. First one is between 2 stations. The second one is between base station and that of the reference clock. So technically, you can have within 1.5 microseconds of each base station, but then these 2 would be greater than 3 microseconds. Those are the type of synchronization errors we're seeing in the field today. And the question that we're being asked is, well, how do we find out where's the problem? I look back at my reference, it says I'm within 1.5, but that tower and that tower, these cells are not communicating, they're greater than 3. Where's the problem? And we'll go into how you find that problem in my next presentation. All right, I've already shared this slide earlier, but just to quickly rehash. If you have GPS, what's the benefits and the drawbacks of that? Well, the first one is obviously, as long as you have open sky, towers set up or cells set up on top of buildings, clear line of sight, you're in pretty good shape, with the exception of once you lose that line of sight, what happens? In the 5G deployments, especially small cell, when we're looking at the street level, that's when you run into the challenge when you don't have clear sky and you can't depend on GPS. That's when you start seeing different requirements there on how do I keep these different radios synchronized when they're at the street level. You'll notice that also risk of jamming and physical damage. It's amazing. You can go on Amazon right now and you can buy a jamming device. I mean, they're not that expensive. People use them for a variety of different reasons, some of them legitimate reasons, most of them not. But it doesn't prevent people from buying jamming devices, and they just leave them in their cars or whatever it may be. And all of a sudden, you're bringing down a tower. So how do we overcome that obstacle? When synchronization is so critical for 5G communication, how do we guarantee we have that? This goes back to my comments I made earlier about IEEE introducing 1588 or Precision Time Protocol. Again, this protocol has been around for a long time. This isn't anything new. This has been used in network synchronization through fiber optic networks from the metro to the core, even in enterprise applications for time-sensitive networks. What we're seeing today, though, is that being able to use PTP, we're able to distribute that timing from a grandmaster clock through the fiber network over Ethernet packets. So how does this work? Again, we discussed this earlier, but just to recite, you start off with your grandmaster receiving that reference, that stratum 0. That's your GPS timing coming straight from the GPS signal. This would be at a secure location. This would have clear line of sight. This would normally have 2 to 3 multiple GPS backups, a very expensive solution, but to be able to guarantee that timing under any condition. Once that timing is received, it is sent through your fiber network through what is called a grandmaster. That grandmaster is responsible for synchronizing that GPS to its primary reference clock source, and it's distributing that timing through Ethernet packets. Now, these are Ethernet packets just like your data packets. Slight differences. One of which, obviously, it's have to have a high priority. This traffic can't be buffered. This traffic has to be able to get through your network because it's carrying your timing information. The way it works is once that packet is received at a PTP-aware device, it strips off that time of day, TOD, and that timing, resyncs it to its own timing, so it verifies that, and then it sends messages back to the grandmaster, so it's a two-way communication, as an acknowledgement. Basically said, I see your packet, this is my time, I'm going to send it back. The grandmaster sees it, and he says, okay, I see the offset, the difference over what your timing was, we'll adjust accordingly, and everyone's okay. Now, this two-way communication isn't just from the grandmaster to the network element, but it's from every network element in between. So it's grandmaster to clock, then grandmaster to clock, then grandmaster to clock, and so on. Now, the clocks in between, and I'll go more into details, they have different categories of clocks, but you have your grandmaster clock, you have your boundary clock, and then you have your slave clocks. And basically just how it sounds, the grandmaster is in charge. The boundary clocks retime off of the grandmaster. And then the boundaries send that clock to the slave, and then the slave retimes off their boundary clock, and so on. So when we take this to the field, and here's when the challenges start. So I have my network. I have my grandmaster clock. I'm sending the timing through my boundary clocks going all the way out to my base station. How do I know my base station is within that 1.5 microseconds? Well, here's a caveat to that. You'll notice in the max timing error, this is what we're measuring here. We're measuring from the grandmaster to that of the base station. But you notice it's only 1.1 microseconds, not 1.5. Why is that? That's because we're timing off of the last network element before the radio. So we're taking into account once you go over the radio, that's where your additional 0.4 to make sure you're within that 1.5 budget. We're measuring at 1.1 microseconds at this point. And we're checking two things. First of which, we're checking to make sure that we're seeing that PTP protocol. Why is that important? Because obviously we're trying to make sure that our endpoint is receiving that timing from the grandmaster. We're also making sure that the network isn't blocking any of those PTP packets, because again, these are Ethernet frames. They can be blocked, they could be buffered, they could be dropped. I mean, that would be worst case. So we're verifying that once we're at that farthest point, the endpoint within either the CRAN hub, this could be at the base station, this could be all the way up to the radio. Are we seeing those PTP packets? Do we see the protocol? The second thing we're measuring is, do we meet that timing error? Are we within the 1.1 microseconds? That's the threshold we're working with. That's 1,100 nanoseconds, and we count every one of them. Because when it comes down to it, that's not a lot of runway to work with. Does this make sense so far? All right.
This scheme is for one network only, but how about there are different networks? How will they synchronize?
So when you say the question is
Like
this,
three carriers, AT&T, T-Mobile.
so much larger sites within radios. So I have a slide coming up in a little bit, and the question is, well, how is this over a larger scale? This is just one leg of one network, right? How do you see this on a grander scale? There's in upcoming slides, I'll show you how this is being deployed in several different types of CRAN environments and a larger scale, and that should answer your question. Other questions? Okay. Oh, it's the next slide. So what I'm identifying here on the left-hand side are 4 different types of RAN scenarios. So again, going back to our xHaul. So if you remember back in the early part of my presentation, I had the slides that showed the CU and the DU and the RU all together. And then I had the RU, the radio unit, and the DU and the CU separated. That's what you're seeing on the left-hand side here. 4G combined with 5G on the top 2. That's the 5G NSA, or non-standalone deployment that Jeff was describing earlier. And then you see the 2 on the bottom, distributed and centralized 5G RAN cloud. That's for 5G NA. 5G SA, standalone. So you have standalone on bottom, non-standalone on top. You notice we use very similar, we're going to start off with the remote radio heads and BBU, just like here, remote radio head and BBU. Here's your CRAN environment. Here's your DRAN environment. Here's where you have your RU, DU, and CU all located at the same spot. Here's where the RU is going over the mobile fronthaul to the DU and then the CU here. So real quick question, quiz question from earlier today. If my RU, my communication from my RU through my DU, instead of being called mobile fronthaul, there's a different name for that. Does anyone remember what that is? From the RU to the DU, I'll give you a hint. There's 1 and 2. NGFI. NGFI, Next Generation Fronthaul Interface. That's NGFI 1 right here. And then when you go down here to the centralized RAN, here's the RU and the DU. That's NGFI 1. The DU to the CU, we called it mobile mid-haul here, but what else is that called? NGFI 2, exactly. So this is just a block diagram showing what this would look like. Now, yes?
So for the MFH, you also have products coming with like over-the-air fronthaul, right?
Mm-hmm.
FTTA and all that. So do you have set up to measure those things?
So things such as like a microwave links as well, or?
Yeah, I mean, it's over-the-air fronthaul basically.
Mm-hmm. Over the.
Also like, FTTA, like fiber suites, they're coming with products like that.
So the question is, so over-the-air type of fronthaul environment, does this apply for over-the-air fronthaul as well? Is that? Yeah, so absolutely. This is the same. So we're using this as a block diagram, and I'm using fiber as the example for this, for the PTP, but that's not to say that this isn't going to be also applicable for over-the-air fronthaul as well. So in the case of here, this could be a microwave link as well. This could be a millimeter backhaul as well, as Jeff mentioned earlier. So those would all apply as well. So I break down these 4. Now you'll notice I don't have any timing in this slide yet. I wanted to show you the 4 different networks first, and now I'm going to add timing to it. So, first slide. This is the first proposal on how you would be able to support timing through a PTP network over 4 different environments using the same grandmaster. So this goes back to your first question. When you're looking at this on a much larger scale, what am I looking at? How many grandmasters? You'll see a couple of different terms here. First, you see the GM, or the grandmaster clock. You see that located from a central office environment. This could be an MSO, this could be a CO, This could be not necessarily a CRAN hub because that's going to apply more to the next example that I'm going to show, but from a central location, and you notice it's going from an edge router through what's called BCs, or boundary clocks. Boundary clocks are important because each one of the boundary clocks retime every time they receive a signal, every time they receive a PTP packet. Now I bring that up because later I'm going to be talking about non-retimed network elements. That falls under a different profile, and we'll talk about that in a little bit. But you'll see each one of these BCs are communicating through to the grandmaster. So grandmaster to BC, BC to BC, BC to BC, BC to BC. Each one of these links to the BCs are a constant communication between the two, adjusting the timing in relation to one another. Finally, you get from the boundary clock going to the SCs. These are the slave clocks. These would be the ones located closest to your radio heads, your remote radio units, or your RUs. This is important because, again, this is what's receiving the timing all the way back here from the grandmaster. Now, what are the benefits of this? First of which, you have one grandmaster distributing the timing, all sharing the same timing source. You also have boundary clocks throughout the network that are constantly being retimed. So you're able to provide resiliency. You can also provide multiple redundancy paths. In the event that you have something fail, you have additional boundary clocks to help support that. What are the drawbacks to this? First of which, the first drawback is, same as the advantage, only having one grandmaster. What happens when you lose that grandmaster? Bad news. You lose all of that goes down that chain. Now, the boundary clocks still have holdover timing that they can hold over and continue that timing, but each one of these boundary clocks would have their own holdover time. Also, the dangerous part to this, and I alluded to this in the earlier presentation during that question. The gentleman had the question about that timing error and why are you measuring this in the field? Well, each boundary clock, as you pass through a boundary clock, you're adding a very little amount of timing error. So the example I like to use for timing error might be a bad example, but those that have children, they'll understand. When you have the kids that play the telephone game, you guys familiar with the telephone game? Where one child starts with a message and they whisper that to another child, and then they whisper it and they whisper it. What happens by the time you get to the end of that message? By the end of that chain, the message is completely changed from how it started. Why? Because each child added a little something different to that message. Timing error works the same way, although not as much fun, but the way it happens is every time the timing, although it's being retimed, and here's how small of an error we're looking at. Every time a PTP packet enters, let's say the router is taking that packet, stripping off the timing, sending that to its clock, comparing that clock, sending it back to a packet, and then sending that packet out. That is where that timing error is coming from. And each manufacturer has a different spec. You're looking at some of the best performing ones. It's in the neighborhood of about 20 nanoseconds of timing error per network element. Per hop, yeah, per each element. So when you look at 20, 40, 60, 1.1 microseconds, that's right. So when you think about that, well, if I have 1,100 nanoseconds to work with, and I'm only adding 20 nanoseconds per network element, I got a lot to do, right? I mean, I could daisy chain these things forever. Well, here's the caveat to that. One, everyone specs best performance. Everybody specs best performance, right? But now you start taking into real world considerations. Little things. For example, asymmetry. Asymmetry between network elements, meaning what happens if I have a network element where the fiber going in one direction from point A to B is 10 kilometers, but the fiber going from B to A is 11 kilometers. Well, my packet is being received faster in one direction than it is going the opposite direction. That affects my timing error. Or the timing error from the antenna, the antenna going from the GPS going through the building to the grandmaster clock. I mean, it takes all these little things into consideration, and I'll show examples of this later on in the testing challenges. But all of these little things add into the total timing error. Another one is when you're changing speeds. Let's say because again, these boundary clocks, these could be routers, this could be switches. Let's say my connection from my edge router to my boundary clock is 10 gigabits per second, but then from boundary clock to boundary clock, it's 1 gigabit per second. Now I'm changing speeds. What happens to my timing error? It's being adjusted because now that traffic is being buffered because I'm going from 10 gig to 1 gig. Does that make sense? All of these changes contribute to timing error. So although 20 nanoseconds sounds great, once you start adding these things, you use up that budget very quickly. So, an alternative solution. All right. You told me that if I had all of these boundary clocks in place, I start adding timing error. How do I reduce timing error? Easy. I add more grandmaster clocks. I put more grandmaster clocks as many different sites as I can, and then distribute that timing only directly to my slave clock, or maybe within 1 to 2 boundary clocks. This is the deployment that we're seeing most often in 5G conversations today. A lot of the providers that we're working with realize I need more grandmaster clocks. That's just all there is to it. Question?
I just noticed something.
Mm-hmm.
You mentioned that there's a 3 microsecond delay or maximum
Between sites,
between two towers, right?
Mm-hmm.
Are we talking about distances of the range of 1 kilometer, or what's the range of distances between towers?
So, are you asking what's the distances?
Between the towers, that's a 3 microsecond. What is the actual distance between towers?
Well, this could be anywhere within an entire region or sector, anywhere that the radios would communicate with one another.
Can it be more than 1 kilometer?
Oh yeah, it could be more than
Then
1
in that
kilometer.
case, there's one problem I've noticed. That is that the speed of light, that's the maximum speed you go at,
Mm-hmm.
is in 3 microseconds, it goes maximum 900 meters.
That's right. But now what we're talking about here, though, is the retiming for each element, right? So what happens is we're not communicating from one tower to the other directly with the timing. These two do not synchronize within 3 microseconds over the air. They're all going from their slave clocks, which are going back to the one source. So what we're looking at here is you still have one grandmaster, or it could be multiple boundary clocks that are constantly retiming. The challenge where you would have the 3 microseconds, where you would see that, is let's say, let me go back to my previous example as a good view to see this. Excuse me. Let's say the network here, this DRAN for 5G, is within the same area as this CRAN for 5G, and these radios need to be synchronized with one another. If this boundary clock going through this route is exceeding its 1 microsecond, 1.1 microsecond, let's say of timing error, it has too many hops, and this one has the right amount, it does not exceed it, this would still look synchronized, where this one would generate alarms. And now these two would not be able to be, even if they're geographically close together or spread apart, their timing link is what's causing them to be outside of the 3 microseconds.
Also, you have to worry about the satellite link also.
Yeah.
If that is, let's say, over 900 meters, then you are off already.
Well, with the satellite link, are you talking about the communication over the air to the grandmaster here?
That will take more than 3 microseconds by itself.
That's only in relation to once the timing reference. So the satellite's providing the timing reference to the grandmaster, and the grandmaster now becomes the PRTC, the primary reference timing clock. So although distance-wise, and it may be an offset but from that of the satellite to the PRTC now becomes my primary, that grandmaster. So we eliminate that offset by using this as the reference, not here. Until it begins there, that's right. This is T0.
Also, there is concept of timing advance, which takes care of distance.
Correct. So when there's, so the question or the point that was made about timing advance or timing offset. where it can calculate the distance based on how long it took the message to get to you. So for example, let's say if two grandmaster clock and a boundary clock are greater than 10 kilometers apart from and connected through fiber. When the boundary clock receives that PTP message, it's going to compare the timing stamp in it compared to its own timing stamp to determine how long it took to get there. It might be 3, could be 30, could be 100 microseconds in that case, depending on distance.
The point would be that in this case, let's say you have 4 of them, 4 towers.
Mm-hmm.
In order to get the 3 microsecond condition, you will require that all 4 of them, the distance between any 2 of them should be less than 900 feet. That's what you will find if you put that condition.
Not necessarily, because again, the 3 microseconds, the difference is still in relation to the or to the boundary clocks that's providing its timing. Remember, they're not providing timing to each other. It's only going through the boundary clocks.
That is correct. But what I mean is, let's say you have accurate retiming. Everything is timed accurately.
Okay.
And the grandmaster clock is, defined by the satellite connection. You get some value, right?
Mm-hmm.
Now, if you have everything accurate, then let's say that the first one is at time 0, okay? First tower,
Okay.
time 0. And the second one is, let's say, 1 kilometer away, right?
Okay.
From the first one. Then don't you think that if the timing is accurate, timing of that one will be 1 kilometer away? If everything is accurate?
Well, I think, and I might be wrong, but you're talking about, you can't take the first tower to the second tower. You're going from the first tower to where the first tower and the second tower share the first boundary clock.
Mm-hmm.
That's the point that needs to be within the 1.1 and 6.
Correct.
So it won't matter if that one's farther from the grandmaster, as long as the shared boundary clock that they hit still falls within that time frame.
Right. Or even if the boundary clocks aren't shared, but as long as the boundary clocks are within that same the time difference between the two to the tower. Exactly.
That is correct. The boundary clocks, let's say if they are getting accurate timing, they are retiming,
Mhm.
everything is accurately done. Then don't you think that the first one, let's say this first one is at 0, distance 0 something,
Okay.
okay. The second one is at distance 1 kilometer, relative distance, I mean.
Relative to the
From
first
from the
tower.
grandmaster.
Oh, from the grandmaster.
Grandmaster, right.
Okay. Okay. I thought you were referring to towers from themselves. Are you talking about distance in relation to the grandmaster?
The grandmaster is in the middle,
Mm-hmm.
and then you have tower 1, let's say at relative position 0,
Mhm.
right? And the tower 2 at relative position with respect to this one, the grandmaster, let's say it's at 1 kilometer, right?
Okay.
So don't you think that this timing will be off from this timing by 1 kilometer?
No, and this is the reason why, if I'm understanding your question correctly. So just to repeat this to everyone, in the example of down here, where these two all share the same boundary clock, the question is, if this tower, in relation to the grandmaster, if this one is about a kilometer farther
Farther than the other one.
than the other tower that it's sharing the same timing, the grandmaster
How
from,
the timing is accurate, let's say.
right? Wouldn't that offset the timing based on the distance?
Yeah, that is timing between those two will be
Between these two, because physically they're two different, they're within our 1 kilometer difference from that of the grandmaster. That's the question, right?
3 microseconds will be off.
So the reason why that would not be is because, and I made this example earlier, is each one of these clocks are communicating with each other, and they adjust the offset of their timing based on their distance to one another.
Correct. Adjusting everything is based upon, their time to communicate, right, or traveling distance.
Correct?
Correct. Based upon that, they are trying to estimate what the actual time is from the satellite, right?
But it's also adjusting the offset based on distance.
But they are trying to get the actual time, right? The time
Correct.
of the satellite. All of them are trying to get the time of the satellite, right?
Yes, that timing is what's being
Let's say
distributed.
that is being done accurately. Everything is done accurately. Right?
Okay.
They all retime it accurately and get the estimated satellite time, right?
Yes.
Right? If that is the case, then I back off. Then they will get it accurately.
Well,
They reassess the time.
right, because the offset, because it has to take into consideration, as you mentioned, if the distance is always going to change, right? You're never going to have two towers equidistant from the same reference point. There's always going to be difference in distance. So the way that the timing adjusts itself, and it's always going to be a different adjustment based on distance, right? The amount of fiber you're going through and so on, or the amount of network elements that you're going through as well. That's why in relation to boundary clocks, and this is a function of the boundary clock, not that of the slave clock, but the boundary clock will determine once that packet is received, and let's say the timestamp says 12:03, and my clock says 12:06, I know that it took 3 seconds for it to get to me. And I adjust my timing now. I send a message back saying it took 3 seconds for me to get your message based on that distance. And once I send the message back, that grandmaster or that previous hop says, okay, it also took me 3 seconds to see your message. So you adjust your clock 3-second offset based on that distance.
I back off.
Okay. If we could discuss it, if I'm not answering your question,
I think you answered it.
Okay. Other questions? Yeah. So going back to this point, again, we're starting it as far as 5G deployment, we're seeing where grandmasters are being deployed closer to the edge, be it within the C-RAN hubs, 5G hubs, in order to have the closest amount of timing and more multiple grandmasters. Now, the downside to this, more expensive. You have to support more grandmaster clocks. The upside to this, less hops, less boundary clocks. So what does that equal? Less timing error, because you're much closer. Now, when you start adding additional synchronization requirements, this is and I'm not going to spend too much time on this, but basically what this is, within the radio itself, this is when it starts getting really tight, specifically for MIMO applications. You can see up here for what they call category A+, the synchronization, so this is your timing error, 65 nanoseconds. Now, this is not going back from that of the radio all the way through your boundary clocks to that of the reference clock. This is just at the radio to the boundary clock itself. This is very close. This is where you're starting to see, this is part of the reason why you see that grandmaster being put directly into that of the C-RAN, to be as close as possible, because if I have an absolute timing error, if I'm going all the way out here of 1.5 or 3 microseconds, I can push that clock a little farther out. But if I have to support applications such as the MIMO here, I don't have much room to work with. Does that make sense? And then this is a similar thing where it's showing it from the transport network. And again, this is just reiterating the same thing, but from a different perspective, being that that's being defined in the eCPRI specification. So what does this mean? This means that this timing requirement, the synchronization, in order to support these applications, this isn't just a 3GPP requirement, but this is being defined by both the eCPRI specification, IEEE, and 3GPP. Okay, so what does this look like in the field? How are we doing this measurement? You're taking a network tester, and this is the Enritsu Network Master Pro. That's this red this box right over here. And there's a couple of things that you need to do. First of which, you need to be able to emulate that grandmaster signal. And what do I mean by that? That means if you're going out to the site, I'm going to the last boundary clock or the last slave clock, I need a reference. I need to look like the grandmaster, but bring it all the way to the far edge. So what you're doing is you're getting a reference signal into that of your network tester, and then you're taking that all the way to your boundary clock, and then you're measuring it out of your boundary clock and verifying the offset. What is that difference in timing error? Here's my reference. Here's what my output looks like. How much of an offset is there? Is it plus nanoseconds? Is it ahead of my reference? Is it minus nanoseconds? Is it behind my reference? Or is it ideal? Over time, you start looking like, you see this, what looks kind of like a graph with a couple of different colors, and I'll zoom in on this on the tester in a little bit. But what you're seeing is how that timing drifts plus or minus nanoseconds over a period of time. Why is that? Well, again, it goes back to my previous comment. PTP are Ethernet frames. Ethernet frames get congested. Ethernet frames get dropped. So Ethernet frames, even if you have a perfectly stable network, those packets are bursty in nature. Now, depending on how you set up your PTP timing, you can do anywhere from 64 frames per second to 128 frames per second. Sometimes even less, like 16 or 32 as well. But typically, you're seeing about 64. Now, when you think about over your bandwidth of 10 gigabits per second, 64 frames in a second really isn't that much bandwidth. You're really looking at it in the neighborhood of about 1% of your total bandwidth. So these things are just, they're very small as far as your bandwidth is concerned. But those 64 frames are all adjusting the time 64 times per second. That's what tries to keep us on our accurate timing. Does that make sense? So going back to our example of doing the testing, you have the tester set up here. You plug it into your PTP network. On the left-hand side, you have your setup as to which protocol that you're supporting. And remember, I made the comment earlier about you have network elements that are PTP aware, and then you have network elements that are PTP non-aware. That'll determine what type of network setting that you're putting in the tester or that you're supporting. So for example, PTP aware, where every one of your network elements is retiming, that's called the G8275.1 profile. If you're going through a network that has PTP aware and PTP unaware devices, or PTP transparent devices, you're going through 8275.2 profile. So the idea behind this is you have to make sure when you're testing this, which one am I measuring? A .1 profile or a .2? When we compare this back to NGFI, rule of thumb, NGFI 1 requires .1 profile. NGFI 2 supports .2 profile. Makes it easy, 1 to 1, 2 to 2. Easy correlation. What you see on the right-hand side here is once you're receiving those PTP frames, you're seeing the information of your grandmaster clock. This is telling you whether your protocol is working or not. Why is that important? In our previous slide, you saw that there could be multiple grandmaster clocks. You could have a primary and a secondary clock. When you're measuring this in the field, you want to make sure that you're looking at the right clock, the primary clock. Or you may test the switchover. What happens when I have a failover and I switch to my backup clock? Am I seeing the right grandmaster clock? That's what this information is down here on the bottom right.
How would you know?
It has an address to it and a name. So just like every Ethernet device has a MAC address, so does your grandmaster clock. And you'll be able to tell by the address on your grandmaster clock whether or not you're looking at the right one or not.
Is the NTP network timing protocol same as PTP?
NTP? NTP, or what is it, 2000, they're similar protocols, yeah. They're both under network synchronization. There is a difference as far as quality of the clock is concerned, where PTP is a little more accurate because it supports both phase and frequency. So that's the big difference versus NTP. Okay, and here's what the field measurement looks like for the second measurement. Now, even if you don't do any measurements in the field, all you have to pay attention to, and you'll see it here, your max time error. This is what's telling you whether or not you are within the 1.1 microseconds or not. At the end of the day, when we're doing this in the field, when we're working with our equipment manufacturers that are doing the measurement, this is all they care about. Now, we provide the additional data up here, that latency asymmetry as well as latency variation. What are those differences? I made the examples earlier. Latency asymmetry is when you have, that is a constant time error, something you can correct or change. What would be a constant time error? Would be something about the, let's say, the mismatch in distances. You have fiber going in one direction, or you have your signal going over 10 kilometers in one direction, 11 kilometers coming back. That's a symmetry. You're always going to have that fixed offset because there's always a difference in length. This is where you would be able to identify what that total distance is in relation in time. How is it affecting my timing? You also have the latency variation on the bottom. That's more of dynamic latency. That's the one such as buffering, congestion, network congestion, depending on how your queues are set up. That's where you would see more of a dynamic adjustment. That'd be a little bit harder to change. Again, it's dynamic in nature. It may not be something you can characterize as well. Versus the constant error, which is latency asymmetry, that's something you can do. And then you see on the right-hand side, as I mentioned, that's the graph over time, how you're changing plus or minus in nanoseconds. We just finished up talking about network synchronization as it related to phase one, and that being the requirement for network synchronization in order to support the enhanced mobile broadband applications as we transition from FDD to TDD. Now I'm going to talk about some of the requirements moving into phase two, as specifically as we're adding the ultra-reliable low latency communication and that of Internet of Things or massive machine-to-machine type communication. You see the two applications being listed here on the bottom, but this is also being in conjunction with that of enhanced mobile broadband. So bringing it all together is the purpose of Release 16. Now, here's something that we took out of the industry, the 5G AA. They're responsible for the applications related to V2X, or vehicle to everything. And what you'll notice here is that in the requirements for autonomous driving, so this is per the standard, you'll see that there's a latency requirement, a reliability requirement, as well as a data rate requirement. So this is very new to the industry, specifically over the air and that of the transport network, because now we're talking about mobile communication requirements for a moving vehicle. Right? This is a fast communication where the vehicle is going to be traveling 65 plus miles per hour, and we have to guarantee things such as latency within 10 milliseconds for the vehicle platooning, remote driving as much as 5 milliseconds, reliability, those that are familiar with the old 5 nines of reliability, we still have to guarantee the 5 nines of availability or reliability, and data rates up into the neighborhood of 53 megabits to 1 gigabit per second. So you're looking at 1 gigabit per second over the air of a moving vehicle with latency less than 3 milliseconds at a 99.999% availability. Yeah, no problem. Piece of cake, right? So this requirement ends up leading into the UR LLC requirement of one-way latency. Now look at this. This is one-way latency, which includes the radio link and network. Okay, so up until this, like I said, until 4G, no such commitment has ever been made for a mobile application up until this standard. Here it is documented in the 3GPP, in case you thought I was lying. It's here listed here as part of UR LLC, as I mentioned, 0.5 milliseconds, or that's 500 microseconds for uplink and 0.5 milliseconds for downlink. So 50 or 500 milliseconds uplink and downlink. Now you'll notice, again, and I put this on purpose, but to also highlight for enhanced mobile broadband, that's the application that we're already supporting today for 5G. That's phase one. 4 milliseconds uplink, 4 milliseconds downlink. This is latency, right? So we're not talking about synchronization, we're talking about latency. See a significant difference in these two requirements that all have to go over the air supporting in the same application. So how do we treat these? Well, first of which, in order for us to do the network latency for, again, these mission critical applications, and we talked about some in the earlier, I'm not going to rehash those, but you'll notice the 500 microseconds for one-way latency, that's between over the air, from the device, over the air, to the radio, over the NGFI 1, so this is your eCPRI or radio over Ethernet, terminating on your DU. So that's your distributive unit. Now, the CU to the server, that you have additional bandwidth. That's the 500 microseconds. So you're still within that within that window. But this one is the tough one, the 50 microseconds unidirectional. So again, going back to Jeff's presentation earlier when he mentioned about not being able to see the IQ data because that's being terminated in the radio. Why? Right there. In order to meet these requirements for this latency, you don't want to have that terminated going through your backhaul in order to terminate that IQ data. You have to have that as close to the radio, if not in the radio, in order to support that requirement, which goes back to those V2X applications in the previous slide. Is this making sense? Okay. This is more of a block diagram. I'm not going to spend too much time on this, but this is basically showing the same thing in the previous slide, but at the different termination points. You'll notice over the air, NGFI 1 and NGFI 2, otherwise known as the F1 interface, for those of you that are familiar with the F1 interface. Here is your requirement of terminating the eCPRI and radio over Ethernet data. So this is eCPRI from the radio unit to the DU. This is where you're getting your IQ data. This has to be within the 50 milliseconds or 50 microseconds. From here, the NGFI2, this is your IP data. This is what falls under that 500 microseconds, so much more latency buffer or latency less of a restriction. I broke this down into the 3 different standards because what you'll notice here, 3 different standards, but all of them are pretty much saying the same thing. And what you're basically looking at here, I identify the different requirements: enhanced mobile broadband, the 4 milliseconds, the URLLC, that's your latency, your V2X, that's your 500 microseconds or 0.5 milliseconds. Again, from here, there's your total 500 microseconds. Your mobile backhaul, you got 10 milliseconds, so you got a lot more space to play with there. But again, it all falls under this 500 microseconds, or when you go down here, the 50 microseconds. So how do we meet that? We take the 3GPP model and we break that into subsections of the DU and CU. Both of these are included in the next generation core, the NGC. All we're doing is we're breaking them down into their logical functions and say, okay, this is the part that has to be, yeah, that's actually a typo there. That should be 500, I apologize. This should be within 100 or 50 microseconds, depending on which requirement you're looking at. And then the rest is the 1 to 3 milliseconds. You have much more space to deal with. So what is this stating? This is basically pointing out the need for latency sensitive applications require latency sensitive measurements. How do we do this? So, similar to how we've done network trafficking, policing, and shaping test measurements in the metro and the core, is the same application we move forward with in the mobile edge or in the NGFI 1 and NGFI 2. In order to simulate these 3 different types of applications, we create different service level agreements for each one, just like how you would in a network itself. You would be provisioning and shaping your network. How we do it is we generate these 3 different types of applications in eCPRI or radio over Ethernet traffic. Basically, our tester has the ability to generate those radio over Ethernet or eCPRI frames, each one with different service level agreements associated with them to simulate enhanced mobile broadband, or we called it a VR or AR application, Internet of Things for machine-to-machine type, or the dreaded V2X application. Now you'll see as it goes through the network, you see the server here and servers here, and this is our virtualized network. This is an explanation of network slicing. Each one has a different priority. Each one is treated differently as it goes through the network. Some of them may terminate in servers closer to the edge. And what would we call this? Anyone remember a server closest to the edge? Mobile edge computing. Correct. This would be terminating my service level agreement for V2X applications as close to the radios as possible. Whereas my machine-to-machine or augmented reality, my enhanced mobile broadband, that may be terminated farther. Why? Because I have less of a latency restriction. Why tie up these resources unless it's a latency critical application? If it's not latency critical, I'll push it further out to my network. Does that make sense? Okay. From a tester's perspective, this is what it looks like. You basically have the tester that, as I mentioned, it generates the eCPRI or radio over Ethernet traffic, each with the different service level agreements to simulate the applications. Goes over as if, treats it like a virtual radio, where that's what our tester is doing. It's generating the traffic as if it was from the radio. And it's sending it through your NGFI 1, possibly NGFI 2, and then terminates that as if the tester is now the virtual MEC, or mobile edge. And we're testing it end to end, as if it's going from the radio to the edge. It's showing the different measurements for latency, min, max, and average, and you see this in microseconds for each application. You'll notice a top one here, 6.7 microseconds versus 117 microseconds. You can easily identify in that application which one is my V2X versus which one is my enhanced mobile broadband, just based on the latency. Now, if it was wrong, and that was my V2X on top, and that was my enhanced mobile broadband on the bottom, I definitely have a problem with my service level, my shaping, right? Because my enhanced mobile broadband is getting there a heck of a lot faster than my V2X. A lot of people are downloading videos in 2 seconds while a lot of cars are crashing. So, what does this look like from a physical perspective? You have your MT1000, you have your 2 different network masters. You notice that we have the synchronization here. I have the GPS. Why is that? Because now I can, again, as I mentioned earlier, similar to how I used my application for synchronization, I have the ability to synchronize my tester to that of a known reference. So I have GPS timing on both instruments. This allows my clocks on my testers to be identical to one another. Why do I want them to be identical? This has nothing to do with synchronization. This has to do with latency. I need to have nanosecond resolution and accuracy for my testers. Otherwise, if they're not nanosecond resolution, what's the point of me taking a measurement if I can't measure nanosecond accuracy with latency? And that concludes the latency part, or the second half of the presentation.